Hello, and welcome to the session on Geodesy and Datums, Part 2, Horizontal and Geometric Datums, being sponsored by the Florida Surveying and Mapping Society, GNSS Users Group. If you saw the previous presentation on the fundamental surfaces in geodesy, you will have already been introduced to several topics such as the reference ellipsoid and the geoid. And I'm going to go into greater depth in a number of areas, both in terms of the reference ellipsoid and its importance, its development for the use of horizontal, or what we now commonly refer to as geometric datums. I'm going to talk more about the process, the historical process of the development of the reference frame, because I think it's important that as we migrate into more contemporary positioning environments, we're still left with legacy data. So I think it's really important to have a connection between what that legacy is about and how it may or may not fit with contemporary positioning activities that we're involved in. So let's again visit the slide that I had. What is a geodetic datum? Right? So this geodetic datum is a set of constants. In the case of a horizontal or geometric datum, it defines the origin of coordinates, the size and shape of the Earth, and the orientation of our coordinates. It's given a name. So for the horizontal datum, the North American datum of 1983, NAD 83, is the singular coordinate system that defines the entire United States. And that includes everything from Maine to California, Alaska to Florida, American Samoa, Guam, Puerto Rico, the Virgin Islands, the Northern Marianas. So the entire United States and all of its territories are covered by one single horizontal datum. Historically, that was not true. And again, I'll talk about that in a little bit later on in this session. In addition, defining the datum, having this definition of its location, the origin of its location, the size and shape of the Earth and all those things, doesn't really do any good if there's not some mechanism by which users can access it, or as is sometimes commonly referred to, is to realize it. So what are those ways to do that? Passive or active control. Again, I'm going to describe the passive and active control and the coordinates that are published with them and how all of this has evolved with time. Coming back to the slide from the previous presentation on the geodetic markers. So we're going to talk in this particular case about those markers which are most commonly found defining the horizontal datum. Now, this is not an absolute truth because many of these markers had multiple different types of uses. They could have been horizontal and or vertical. They could have, a gravity mark could easily be also a geodetic marker for horizontal positioning. So realize this is not an absolute, but it's a generalization that the different types of markers had specific meaning and defined specific activities. So since this is a presentation on the horizontal or geometric datums, that's what I'm going to talk about here. So commonly when these field crews would go out and perform their measurements, they would leave behind a survey mark, typically, not always, but typically a brass, bronze, or aluminum disc embedded in concrete, in a concrete post, a pillar, in bedrock, or some other very, very stable structure, something that's not going to move. Right? Because they're going to do a lot of activity. You'll see some images here in a little bit about the activities that they had to go through to perform the measurements. And to understand, if you're going to go through all of those measurement procedures, it was vitally important to leave behind something that was reasonably permanent so that others could come behind and access those coordinates or heights if it was a vertical datum. So traditionally, the Coast and Geodetic Survey, now the National Geodetic Survey, would employ the use of a station that was called triangulation. A triangulation disc had a little triangle in the center, makes it nice and simple, right? And it says triangulation station on it. When the mark would actually be set, and again, not an absolute, but in most cases, and you often find them set in a concrete post. and this post is about 12 to 14 inches in diameter, or it could be square, and it's embedded in the ground about 3.5 to 4 feet. Below that, below the center dot in this mark, there's most oftentimes another mark, just like it, an underground mark. So that if the surface mark was disturbed or destroyed, the value of its position was not lost because there was an underground mark, and you simply had to remove the several hundred pounds of concrete, that the mark was set in, but the values were preserved. That was a very, very important aspect of this. Let's preserve as much as possible those marks. In addition, typically, they would set 2 reference marks. So these are marks that have a little arrow on them, and they do say reference mark. And in most cases, they were set within about 100 to 150 feet of the triangulation station, with their little arrow pointing back at the triangulation station. And in the data sheet, the information that you would get from the National Geodetic Survey, there will be a description of these marks. And it will tell you how far away they are. And it will tell you what they look like. Oh, it's a disc set in concrete, or it's a disc set in bedrock, or whatever it happens to be. And there will be a distance and direction, so that if you happen to go to the field and you're looking for the triangulation station, but you don't find it, but you do happen to fall across one or both of the reference marks, if you have that information, those distances and directions, you could pull a tape and hopefully come back to the original location. And if the mark itself is not there, then you could dig down and find the underground. Or if you didn't find that, if you had those informations, you could create another point that was in the same location as the original triangulation station. So there's a lot of concrete in the ground out here. In addition, again, not absolute, but in most cases, beginning in about the 1930s, 33, 34, the Coast and Geodetic Survey started setting a mark at some distance, usually about 1/4 mile. It's referred to as an azimuth mark. Another disc, there we go, another disc with an arrow in it, about 1/4 mile away, the arrow pointing back to the triangulation station, and it provided a line of known azimuth or orientation. So the idea here being that land surveyor comes to use the survey monument, they have horizontal control, they've got latitude and longitude, they've got northing and easting state plane coordinates, or X and Y coordinates as they were back in the older datums. And they also have orientation, or a line of known azimuth to the azimuth mark. So the surveyor has all the information that they need to begin their new survey without having to go to a lot of extra effort. So there are literally hundreds of thousands of these types of marks that are over there. And they changed in their design when the Coast and Geodetic Survey became the National Ocean Service in 1970, and the National Geodetic Survey was created. They changed the marks a little bit, but they still have a triangle in them or an arrow. So you'll still see similar type marks. One thing I do like to point out in a conversation like this, during my career at the National Geodetic Survey, my 40 years at NGS, I very, very often came into contact with surveyors and others who said, hey, I went to the field and I found a mark. I found one of your marks, and I can't find any information from NGS. Can you help me out? And of course, sure, give me some information. Where is the mark? Or, was there any stamping on the top of it? How's it designated? Et cetera, et cetera. And usually within a few seconds, after a little brief conversation, what I find is, oh, it's not a Coast and Geodetic Survey mark. It was one from the U.S. Geological Survey, USGS. And it is quite common, unfortunately, for many, many users to misidentify the 2 acronyms, USC&GS, USGS. U.S. Geological Survey, up until about the 1980s or so, put in thousands of monuments across the country, but they were always subordinate to the marks that were placed by the Coast and Geodetic Survey, now the National Geodetic Survey, because they were used to perform or to provide the foundation, the control for the USGS topographic mapping effort. So it's really kind of important to understand that there's lots of data out there from many, many other institutions, other federal institutions too, U.S. Army Corps of Engineers, TVA, I mean, the list goes on, that their data may not be part of this national reference frame. So the user has to be a little careful when picking data. So let's talk about a horizontal datum. What is a datum? Well, there are whole academic degrees that are built around horizontal and vertical datums. And we're only going to touch the surface of it here. But basically, there are these 8 constants. And if you know these 8, you know the game. And by saying the name of a datum, so if I say, for example, NAD 83 or NAD 27, I am defining these 8 constants. So 3 define the location of the origin of the coordinate system. So let's look at our national datums for the United States. Today, the national system is referred to as the North American Datum of 1983. It replaced the North American Datum of 1927, or NAD 27. So let me describe those two, because they are the two most important that we see in the conterminous U.S. And while we had NAD 27 in the lower 48 in Alaska, we had other datums in Hawaii and Puerto Rico and America and Samoa and Guam, and I'm not going to go into those in great detail right now. If I talk about NAD 27 and NAD 83, it's the same thing as what happened in Puerto Rico and Hawaii and American Samoa. So if we look at NAD 27, 8 basic constants, 3 defining the location of the origin of the coordinate system. There happens to be a survey mark, one survey monument in the middle of a farmer's field in Kansas, referred to as Meade's Ranch. So this survey monument, which was established as part of the transcontinental arc of triangulation, it was connecting the East Coast and the West Coast. The Coast and Geodetic Survey adopted it as the centroid of the geodetic network, not the centroid of the United States. It's close to that, but it's not. It's the centroid of the geodetic network. And its coordinates, latitude, longitude, and ellipsoid height, were defined. And then every other NAD 27 coordinate in the United States, or that used NAD 27, Canadians as well, and the Mexicans, was referenced to that one survey mark with those 3 coordinates, latitude, longitude, and its ellipsoid height. 3 define the orientation of the coordinate system. So at Meade's Ranch, in that farmer's field in Kansas, now the orientation being the azimuth or direction to another station, in this case, the next station in the geodetic network, which is called Waldo. That's 1. What are the other 2? Well, if you remember my presentation, the previous one, the geodetic surfaces, I talked about the deflection of the vertical. Those are the other 2, the deflection of the vertical at the point Meade's Ranch, Kansas. And the last 2 define the size and shape of the Earth that's used. So in the case of NAD 27, the mathematical model that was used is called Clark, that's Clark with an E, named after Alexander Ross Clark, the great English geodesist. Alexander Ross Clark's model of 1866 most closely approximates the size and shape of North America. You'll see that in more detail in a moment. So when I say I have a coordinate NAD 27, by definition, I'm providing these 8 constants. I'm telling you that. If I look at NAD 83, there are 8 constants, but they're entirely different. Instead of being a survey mark located in the middle of that farmer's field in Kansas, it's now the location of Earth geocenter, or at least as closely as we could approximate that, given the technology that was available circa late 70s, early 80s. Where is Earth geocenter? Well, why go from a survey mark, a passive mark in the ground, to a mark you can't go to, a place you can't go to, Earth geocenter? Why do that? The other system worked quite well. Well, in that migration in the late 70s and 80s, and this is even before GPS was a reality, The National Geodetic Survey certainly understood that the future was going to be space-based. And the satellites do not orbit about a survey mark in a farmer's field in Kansas. They orbit about Earth geocenter. Where is that? How do we find it? Well, you can't go there, so you have to deduce its location from measurements. And given the times, given the information that was available to us circa late 70s, early 80s, our knowledge of the location of Earth geocenter was about 2 meters, about 7 feet. Not bad, it's a big planet. So we have three coordinates there, and they're not latitude, longitude, and ellipsoid height. They're now a geocentric 3D Cartesian coordinate system, X, Y, and Z, much like we would have learned in high school geometry or trigonometry. So it's an X, Y, and Z coordinate system defined at Earth geocenter. Okay, what's the orientation? There's no azimuth, there's no other survey mark. Well, now the orientation, again, is not to a survey mark, but it's global, it's Earth orientation. So imagine, if you will, standing at Earth geocenter, what are the elements that define such a coordinate system? Well, if I happen to be, for the moment, standing at Earth geocenter, and I have an X, Y, and Z coordinate system, if I define Z as up, remember Z is not height, Z is up. It's a difference. Z going from my point, which is Earth geocenter, through me, through the north rotational pole, and of course, south through the south rotational pole. All right, so that's one. X, well, now I can make X go anywhere I want. Well, by definition, institutions around the world had adopted Greenwich as the origin of coordinates, the origin of longitude for the Earth. So if we nominally define that this is going to be the meridian passing from the North Pole, going through Greenwich, and to the South Pole, and along the plane of the equator, it's going to be my x-axis. We think, well, okay, x is in the plane of the origin of the meridian passing through Greenwich. The meridian through Greenwich is a whole other story. We don't have time for it today, regrettably. And then y is simply orthogonal, 90 degrees orthogonal to that, positive to the west. So now I have a three-dimensional coordinate system. And I have my orientation. And the two decide the size and shape of the Earth. So it's the same process, it's just using different points. One is a mark in a farmer's field, another is Earth geocenter. Let's take a quick look at the ellipsoids that have been used in the United States. So if I go to the board here for a moment, in the late 1840s, 1847, 1848, the Coast Survey adopted the use of a size and shape of the Earth known as Bessel. Bessel was a German mathematician. Bessel's model of 1841, and here you see the size and shape A and 1 over F from the previous discussion on geodetic surfaces. Bessel's model most closely approximates the size and shape of the east coast of the United States. Well, why that limitation? Well, that's where all the surveying was being done. The country was expanding rapidly, but the vast majority of all the geodetic surveying that was being done at that time was being done primarily along the East Coast, building the foundation for the important nautical charts that were to be referenced to them. It wasn't until later, after we acquire California, and the Coast Survey sends field units to California to perform measurements, that they get out there, they're making measurements, and they're saying, hey, Bessel doesn't work so well out here on the West Coast. So beginning in the middle 1870s, the Coast and Geodetic Survey now starts a survey that's going to connect the East Coast and the West Coast, referred to as the transcontinental arc of triangulation. And it takes the better part of almost 20 years to complete this survey across the United States. And as that is evolving, the scientists, the geodesists at the Coast and Geodetic Survey then, they're able to look at that data and they say, gee, we have a better idea now of what the size and shape of the United States looks like. Not North America, but just the United States. So in 1880, the Coast and Geodetic Survey adopts Clark 1866, Alexander Ross Clark's model of 1866, that most closely approximates the size and shape of the United States, later also adopted by the Canadians, so it best fits North America. It still does. To this day, it still does. And that was the system that the various coordinate values, the datums that followed on from that, the US standard datum, the North American datum of 1927, and the multitudes of datums around the rest of the world, around the rest of the country, all used Clark 1866 because it was the common surface that the Coast and Geodetic Survey had defined. Beginning in the late 70s, as the National Geodetic Survey is looking at the redefinition of the national coordinate system, a significant debate ensued. That is, what mathematical model for the ellipse are we going to use for this new coordinate system? Clark 1866 has served us very, very well for a long time. Why don't we just keep on using it? Well, the realization was that the future was going to be space-based. Now, mind you, late 70s, no one could fully appreciate what GPS was going to do and how fast that was going to happen. But we did know the future was going to be space-based. So, at a meeting of the International Union of Geodesy and Geophysics, Canberra, Australia, in 1979, the international standard, now known as Geodetic Reference System 1980, or GRS 80, is adopted. And the National Geodetic Survey says that's the international standard, that is what we're going to use. And to this day, it is still the international standard. So countries around the world are all using GRS 80, and at least to my knowledge, there are no significant efforts underway to replace it with anything else. So our national datum today, when we define NAD 83, by definition, we are saying, oh, it's using Geodetic Reference System 1980. It is saying that the origin of coordinates is at Earth geocenter, as best we could determine them circa late 70s, early 80s, and that the orientation of the coordinate system as it was defined on January the 1st, 1984. Those are all elements that are defined when you say, I have a coordinate in NAD 83. Now, that being said, if there were no others we had to worry about, we wouldn't have a problem. But particularly in the community of the multitude of users of GPS, GNSS, where now a conflict often comes up. And that is understanding or having a feeling for the system that is defined specifically for GPS, the Global Positioning System. And that is World Geodetic System 1984, which is defined by the US Defense Department. So this is an international standard, which is what the National Geodetic Survey uses. This is the standard for GPS that was defined at the time by the Defense Mapping Agency. Today that's the National Geospatial Intelligence Agency. And it's used exclusively for GPS. So at this point we are only talking about, and this is important, this is really important, there are 8 components of a datum defining your coordinates. Only 2 of them define the size and shape of the Earth. So that's important. Remember that. NAD 83 coordinates defined using Geodetic Reference System 1980. Many people reporting coordinates in WGS 84, it uses an ellipsoid called WGS 84. That's where things can often become a little confusing because the name of the datum and the name of the ellipsoid are the same. So we have to kind of walk through this carefully. Let's look at the reference ellipsoids just by themselves. NAD 83, the National Horizontal Geometric Datum of the United States, using Geodetic Reference System 1980. The semi-major axis, 6,378,137 meters, okay. The flattening, 298.257,222,101, okay, fine. Let's look at WGS84. A, 6,378,137, well, that's identical. It's the same value. So far, batting 1,000. Let's look at the flattening, 298.257,223,563. Now we have this minor difference in the flattening. What does that mean? What is this difference, this numerical difference out here between these two? How much of a difference is that, practically speaking? One of the functions I was given by my supervisor when these data were reported by the Defense Department in 1987 was to determine, well, exactly that. What does it mean? One of the computations I performed was to compute the distance between two marks using Geodetic Reference System 1980. And I selected a point near Point Barrow, Alaska, as far north as we can go. Another in the Dry Tortugas off the southern coast of Florida. So I computed a distance. This is a continental scale distance. I then went back and changed the computation to reflect the values from WGS84. I didn't need to change the semi-major axis because it's identical. I changed simply the value for the flattening and I recomputed that distance. It changed the distance from Point Barrow to the Dry Tortugas by less than 1/10 of a millimeter. So for all practical purposes, there is no difference in the size and shape of the Earth, and that is really important to remember. That does not mean, however, that there is not a positional difference between coordinates in NAD83 and coordinates defined in WGS84. And that goes back to those other 6 components. What is the origin of NAD83 versus the origin of WGS84? What's the orientation of NAD83 compared to the orientation of WGS84? These are critical components to kind of have a handle on. So here we see, bringing this together, a conceptualization of this process. We have our older system based on Clark 1866, which is modeled on a small piece of the Earth, the United States, later North America, combining with the Canadians. So it best fits this little piece of geography. But nobody cares about what it's doing on the other side of the world. They don't care. Couldn't measure there, couldn't map there. It's not the responsibility of the Coast Survey to do that. With the adoption of a global system, now we can no longer rely on one that best fits one little piece of the Earth. We have to adopt something that is more globally best fitting. So GRS80/WGS84, remember I've already said that they are effectively the same, now is our best globally fitting reference ellipse, but it may not fit North America as precisely as Clark 1866 did. So these are some of the giveaways that you have to deal with when you're realizing something in a global reference frame. So let's take a look now at the historical development. I talked about that and I briefly mentioned it in the previous session on geodetic surfaces. I want to go into a bit more detail. I've already introduced you in the previous session to Ferdinand Hassler, the first superintendent of the Survey of the Coast, and it is from this gentleman that the original triangulation, the foundational data that today is still preserved as part of the National Spatial Reference System. He creates this. On a side note, it's important to note his other incredible contribution to this country. Not only the being a superintendent of the Coast Survey, but he is, through him, the creation of our National Bureau of Standards, today the National Institute of Standards and Technology. So all the standards that we use in this country, the development of distance standards and weight standards and liquid standards, all come from Ferdinand Hassler. Just a brief side note. So Hassler goes to the field and he makes his first survey in 1816. So he's selected as the superintendent in 1807, but he can't go to the field until 1816. Why? Because the equipment doesn't exist. The tools that he needs do not exist in the United States. So Hassler goes to Europe. He's acquiring the equipment that he knows he needs The War of 1812 breaks out. He's caught over in England, so he doesn't get to come back and start until 1816. And he begins this process that went on until 1984, and that's referred to as triangulation. Now, any number of those watching this session might know what that is, but for the benefit of those who do not, triangulation in its conceptualization is quite simple and I think quite brilliant. What you see here is just a diagram giving you an idea of what a triangulation network might look like. The individual little triangles would be one of those survey monuments that I mentioned previously. And the blue lines are lines that were actually observed. That is, a surveyor went to this point, set up an instrument, a theodolite, that measures directions, angular distance, directions, and that person would then measure the angular difference through all of these triangles. And then somebody else would go to another one, and consequently, so you would have, in its simplest form, you would have a triangle defined. So let's look at this one over here. Surveyor would go out, you'd have 3 surveyors, they would measure the angles of this triangle, and realizing that a triangle, the angles of a triangle have to amount to 180 degrees. Mind you, there's curvature of the earth, and so we're really dealing with slightly different math, but let's just take it as simple as possible for the moment. If I know these angles, then I know the 3 angles of the triangle. But these are long distances. They might be 10, 15, 20, in some areas, 40, 50, 60, 80, 100 miles. How am I going to measure that? I need to have at least one distance that I know. So before the advent of GPS, they would take a lot of time to actually measure the distance between 2 of those points. It's referred to as a baseline. Today in GPS, GNSS, we refer to as a baseline as the vector between 2 points. Well, this is very similar. It's the measured distance between 2 points. So they would go out and they would measure a distance here, and then somewhere else in this network they would have another measurement. And if I know this distance and I know the angles, I can then, through the law of sines, I can compute the distances along these other lines, and so on, and so on, and so on. And if I happen to know the coordinates of this point, and its orientation, or its azimuth, and I now know the angular difference to this point, and the distance, I can now compute the coordinates of that point. And so on, and so on, and so on, and so on. It just repeats itself. And then when I would get over here, I would have a new baseline, and whatever the difference between the computed value and the measured value could be removed or modulated out in the process of a least squares adjustment of all of the angles and distances. And I'm not going to spend a lot of time going into the depth of that. This is the kind of presentation that could take entire days to talk about. But here is just a basic, very simple picture of what this is. Now I'm going to give you a picture of a little piece of reality. This is a network, just happens to be the state of Maryland and the state of Delaware. Look how congested it is. These are all the geodetic survey monuments, the triangulation stations that are in the states of Maryland and Delaware, and of course a little bit up into West Virginia and Pennsylvania. But some things to note here, you see the lines between the stations, the observed lines where the surveyor would actually measure the angular difference, the angular direction. The dark lines that you see right here and several over here, these are the actual measured distances. And the measurement distances were very, very time consuming. And we'll talk a little bit about that in a few minutes. So let's look at the datums, the number of datums we've had in the United States. Most people think about, oh, well, we have NAD 83 today, and maybe they know something about NAD 27, the datum that it replaced. That's only 2 of the 24 that we have had in the United States. First was not really a consistent datum set, but it was a series of coordinates that were defined by individual astronomical measurements at primarily along the East Coast, Gulf, and West Coast that were all defined on this Bessel ellipsoid. The first realization of a regional definition was called the New England datum, and it was kind of a test for where the Coast Survey knew they were going to have to go to complete a nationwide coordinate system, because they knew that was coming up. So beginning in 1879 and lasting until 1900, they compute a local datum that says New England, but interesting enough, its origin, remember I talked about the origin for that point out in a farmer's field in Kansas for NAD 27? Well, the origin point for the New England datum is a station called Principio, and it happens to be in Maryland. But the coordinates were never published in Maryland. Kind of an interesting artifact there. The first national horizontal datum for the United States appears in 1900. It's referred to as the U.S. Standard Datum, and it's using Clark 1866. Its origin is Meade's Ranch, and its orientation is that azimuth to Station Waldo. In reasonably short order, it is also adopted by the Canadians in 1913. So the name has changed. There's no change in coordinates, it's just a change in name. It becomes the North American datum, again, Clark 1866, origin at Meade's Ranch. And later, because so much survey work was done after 1913, that by 1927 it was obvious a readjustment, a reanalysis of all of this data need to occur. So the Coast and Geodetic Survey, working with Geodetic Survey Canada, produced the North American datum of 1927, or NAD 27, again using Clark 1866 and still holding the original station, Meade's Ranch, Kansas. At the time that is going on, many other parts of the country are also being surveyed, but they're not connected directly to North America. So we have Alaska, for example. The United States acquires Alaska. The area needs to be mapped. They need to have nautical charts primarily. So the Coast and Geodetic Survey sends field crews to Alaska to start making these measurements. But it's not a systematic process. They don't start in California and start surveying up to Alaska. They go to Alaska and they make individual measurements wherever they're most needed at that time. So individual datums pop up for which the nautical charts are all defined. And in Alaska, there were 14 different ones. And for many, many years, that was okay, because it was all about nautical charting and nobody really cared. It wasn't till World War II comes along that it becomes obvious that it's important to know consistent coordinates throughout the United States. And that began the impetus to include all of the triangulation in Alaska also into the NAD 27. So by 1954, these 14 different datums in Alaska are all combined into the NAD 27. The other areas that are important to the United States, Puerto Rico and the U.S. Virgin Islands, they have their own local datum. Remember, we're talking about a technology that's line of sight. If I can't see from one point to the next, then I can't be in the same datum. And I don't care how large a structure you build in Florida, you cannot see Puerto Rico and the Virgin Islands. You can't see Hawaii from California. So each of these areas had their own local datums. Puerto Rico and the U.S. Virgin Islands were under the Puerto Rico datum. Hawaii had the old Hawaiian datum, and then American Samoa and Guam had their own local datums. It's not till the advent of GPS that now we're able to combine all of these disparate areas together in a single coordinate system. And all of that today is based on the North American datum of 1983, defined in 1983, permanently adopted in 1986. And it's the very first to use that GRS 80 ellipse. It was also the first datum anywhere in the world, civilian datum anywhere in the world, to have its origin of coordinates at or near Earth geocenter. So there's a list of the 24 datums. Let's take a few minutes and go through the historical development, just some images to give you a perspective of what had to happen. So we're going to travel all the way back in time now to about 1816. And this is an image produced by Ferdinand Hassler's daughter Caroline of the drawing of his great theodolite, his 24-inch theodolite that he had acquired in England from a company, Troughton and Sims. Very, very heavy piece of equipment. He was the only one that was ever allowed to use it. So consequently, the process of the survey was very, very slow. And you see in the background this wagon, specially designed just to hold that great theodolite. Regrettably, the theodolite was damaged beyond repair in a great storm that also ultimately was the cause of Hassler's death. But for many, many years, the process of performing the survey was quite slow because the instrumentation was quite large and our ability to get around was very, very limited. I've got some other pictures here that I just hopefully give you a perspective on. Here we see a station up in Utah. Notice the large wall of stones that they had to put up on top of a mountain peak, to keep wind away from the instrument. They had to put up a special tent to keep sun off of the instrument. At least back then, many of the observations were done during the daytime, so that was an important aspect of it. Just an interesting side piece. Most of this wall is actually still in place today. One of the most important elements of producing a survey of this nature was to get as much as we could out of that line of sight. So remember, no satellites. Our line of sight is purely terrestrial. How far can I see on the ground? Well, all you have to do is walk outside, and we all know that typically you're not going to be able to see too terribly far unless you happen to be on top of a 12,000-foot peak in Utah. Right? You're just not going to be able to do it. So one of the creative ways that geodetic surveyors got around this was to build towers. And here you see pictures of wooden towers. These are towers that were constructed, again, particularly out of wood, incredibly expensive, oftentimes well over 100 feet tall. And what I want you to notice is that there's really two towers. So the survey mark itself is actually down here on the ground. The tower would be, two towers would be constructed, the inner one which would hold the instrument or the signal, as in this case, and a platform from which the observer could walk around without ever touching the inner tower except with his fingers to move the instrument. So that there was very, very little personal interaction between the observer and the instrument, and often cases well over 100 feet tall, made out of lumber, out of wood, and if you happen to be in an area where there were lots of trees, well, it was probably a little bit easier to do. The problem, of course, and I think it's pretty obvious, is that this is really expensive and really time-consuming. And if you're in an area, particularly like the Midwest of the United States, where you don't have a lot of trees, then all of this material has to be brought along by the survey crews. So the Coast and Geodetic Survey really struggled to be able to perpetuate the survey very, very rapidly because of this limitation. You have to build these towers to get up over our existing infrastructure, the hills and trees and buildings, whatever it happened to be. So it was important to find some way to get around that as quickly as possible. Well, one of the things about the Coast and Geodetic Survey that many people do not appreciate is that over its history, it has had a huge number of monumentally qualified scientists in geodesy and geophysics, and quite a number of incredible engineers who, while not having advanced degrees, nonetheless performed efforts that vastly improved the capacity of the survey. And just my personal favorite is this gentleman known as Jasper Bilby. Now, Jasper Bilby, this gentleman here, is hired out of a farm in Indiana. He joins the Coast Survey as a signalman. His job is to go to the field and to determine how tall those towers need to be so they can see each other. And in this next image, you see a picture of Jasper up on a pole trying to make those observations. So Jasper was quite a guy. It's quite a tall pole. Well, in the early 1920s, Jasper comes up with a revolutionary idea. Instead of creating the towers out of wood, I'm going to make them out of steel. And that one change alone, that one invention, if you will, now commonly referred to as the Bilby Tower, made an incredible improvement in the capacity of the Coast and Geodetic Survey to produce the geodetic network. And it saved millions of dollars, and our old buddy Jasper here was actually awarded a Commerce Gold Medal by the Secretary of Commerce at the time, Hoover, who later became president. So the process was now we build these towers out of steel, and now you could move the tower anywhere you wanted to. In a few hours, a good qualified crew could put up a 100-foot tower, make your observations for 2 or 3 or 4 days, whatever it took, tear the tower down, put it back in a truck, move it to the next place that you wanted. So that was an important development. There you see the observer up there with a T3, an instrument was capable of measuring directions to 0.2 of an arc second. Here you see just a few images of different types of observations and instruments that were a general part of the process of triangulation. I particularly like this picture of the coast surveyors that happens to be in a peak in Idaho. Got a wooden stand built up. It's secured with these very, very heavy rocks. Literally about 10 minutes after this photo was taken, a lightning strike hit there and destroyed the whole station. Fortunately, nobody was hurt. Larger instruments that come along later for making astronomic observations, such as the VIL T4. So the Coast and Geodetic Survey is, over time, adapting to changes in positioning and measurement technology that have led us, even to this day, to a constant change and looking for the best process of making any of these measurements. So I'm highlighting just a few images here. I particularly like this one. What you see are the ends of 2 bars. They were referred to as baseline apparatus bars. So that baseline that I mentioned previously in the triangulation, vitally important that that be measured as accurately as possible. Circa the late 1980s, the typical surveyor measured with a Gunter's chain, which was not terribly accurate. But now, these bars, which were created by the Coast and Geodetic Survey, could be laid end to end. What you see here are just the ends of them. There are 2 bars that are 5 meters long. They weigh roughly about 200 pounds. And they are laid end to end to end to end to end to measure one of those baselines. Here you see a picture of them performing the measurement at the Salina, Kansas baseline, 1896. Notice that the baseline is only 4 miles long, but it took 5 weeks to make the measurement. But look at the quality, 8 millimeters, 1 part in 720,000 plus. Side note, the survey monuments at the ends, the 2 endpoints of that baseline, are still in place today. And some years ago, the Kansas Society of Land Surveyors actually performed measurements over those 2 lines, and they match the original measurement down to just a couple of centimeters. So the measurement process takes time to evolve. Around the turn of the century, the last century, we see the introduction of the steel tape. Now the distances, instead of being measured 5 meters at a time, can now be measured 50 meters at a time or 30 meters at a time. Those were the 2 standards that the Coast Survey used. But you still had to walk the ground. So it was still very much a terrestrial measurement process. There's some interesting images here of the team measuring through this guy's house or having to build little stands to cross a valley. So it was a very time-consuming process just to measure one of those baselines. After World War II, we see the introduction of electronic technology, and this is where change starts to happen and continues to this day. Beginning in the late 40s, we see the measurement of the ability to measure distances by microwave from the teleurometer coming out of South Africa, and light wave coming from Sweden, the geodometer. And here you just see some examples of those instruments. But something important about them. Now, you no longer have to walk the ground. You can make the measurements over long distances, in some cases well over 50, 70. I think the longest distance that the Coast and Geodetic Survey ever actually measured was about 94 miles long. But what I want you to notice is how big they are. They're big, they're expensive, and they take a lot of time to learn how to use properly. It's not until much later we start to see some of them get a little bit smaller. This Model 6 geodometer over here, you started to see a few surveyors use that. It's not until about 1969, 1970, with the advent of the Hewlett-Packard, the HP 3800, that now we see electronic distance measuring equipment part of the capacity for the average surveyor to go out and measure those distances. And of course today that's all incorporated into a total station. But it was part of these changes in positioning technology that forced the National Geodetic Survey to reevaluate our national reference frame and to perform the readjustment, the development of the NAD-83. By 1984, the use of GPS has become so prevalent that NGS stops doing triangulation and moves directly into GPS only. So those towers and all that other equipment, that goes away, gets completely replaced by GPS. But it's important to note that GPS does not just appear one day, right? It evolves. So if we go back to the earliest launches of satellites, including Sputnik, it was obvious from the launch of Sputnik in 1957 that with some analysis, if you knew where that satellite was in space, you could now position yourself on the ground. So beginning in the 1960s with the launch of the ECHO satellite, the ECHO satellite was set up. It was just a big ball, a lot of reflective surface area, very, very bright. I can remember standing in my front yard, 13 years old, 1964, and watching the ECHO satellite transit over, and brighter than Venus. It was quite amazing. But even though it was being used for telecommunications, the Coast and Geodetic Survey figured out a way to utilize it to perform global measurements. So with launches of ECHO 2 and later PAGEOS, which was specifically designed for space-based positioning, the Coast Survey begins the process of a global triangulation network. So again, triangulation is still part of it, but instead of being terrestrial observations line of sight on the ground, it's now line of sight to satellites in space. In this case, the ECHO and later the PAGEOS satellites, done with very specialized cameras that you see here, going around the world. Notice the areas it didn't go to. So this is during the time of the Cold War. There are no observations in the Soviet Union or countries associated with them, or even China. But the Coast Survey would go around, they would establish these stations in places around the world, and they would observe the passage of these satellites and on glass plates. So they actually take a picture of the satellite on glass plates that was sent in to the headquarters of the Coast and Geodetic Survey in Washington, D.C., and from there a computation could be performed to compute coordinates around the world. While the Coast and Geodetic Survey is doing this, and behind closed doors, the U.S. Navy is doing their own research, which later becomes the NAVSAT transit system, commonly referred to as Doppler. The idea here, the Navy wants to know where all their ships are. So with one pass of one of these Doppler satellites, they would know the location of any ship, primarily nuclear submarines, to within about 100 meters, which was way better than anything that they could have ever known previously. Doppler is really the foundation for GPS. And from this point in time, now we start to see terrestrial measurement systems that are looking at interstellar observational techniques all coming together. We see the development of VLBI, Very Long Baseline Interferometry, which looks at quasars out at the ends of the known universe, and combining that with the transit Doppler. This is the heart of the original NAD-83. So now with VLBI, we can make measurements across continental scales accurate to a few millimeters, and have positional accuracy with the Doppler at no worse than 1 meter on continental scales. So when we produce the NAD83, we see a few differences. Positional differences in the United States amounting from about 10 meters in the area around the Great Lakes to over 100 meters in California, over 200 meters in Alaska, Puerto Rico, and the Virgin Islands, and over 400 meters in Hawaii. NAD83 is only on the books from 1986, and very shortly thereafter, the development of GPS is so rapid that we very quickly understand, okay, we have some major problems. So we have to go back and resurvey the country. And these problems were identified as these four major issues. Points were not GPSable. Well, the term never existed before because we had no GPS. Station accessibility, how can I go and get to the station? Irregularly spaced, and positional accuracy. It was very, very apparent, even in the earliest days, that GPS would provide vastly superior capability in positioning than what we had previously enjoyed with triangulation. So beginning in 1989, the National Geodetic Survey starts out on a resurvey of the entire United States using GPS only. It's referred to as the High Precision GPS Network. In 1972, the name is changed to the High Accuracy Reference Network, so the acronyms HARN and HPGN, you'll see them out there. But now because GPS is being used, everything has to be GPSable, naturally. Try to make the stations easily accessible and regularly spaced. And the agency had to create new orders of accuracy that never existed before. A order, 1 part in 10 million, which basically meant you sat on the point for 3 days, 3 sessions, 5.5 hours. Or B order, 1 part in a million, 2 days, or 2 sessions, 5.5 hours. By 1997, the technology of GPS has changed so dramatically from 1989 that all of a sudden there are errors that were now never existed before now creep into the network. So by 1997, when the National Geodetic Survey was planning on bringing all of this data together, it became apparent that because of these changes, we had more satellites, we had better orbits, the technology was vastly better than it had ever been, and we had the introduction of continuously operating reference stations. So the National Geodetic Survey begins the process of re-observing the country one more time, and this will never happen again. Now they have more state partners, people that they can associate with to produce the HARNs, remove these earliest distortions of upwards of 10 centimeters, which were pretty phenomenal at that time. I mean, being able to measure 10 centimeters on a network accuracy with triangulation was unheard of. So we ensure the connection to the cores, and most importantly, improve the quality of the ellipsoid heights, because that's now the most important part of the element to produce high accuracy heights. Just as an encapsulation of GPS, so we know where we're coming from here. The first satellite gets launched in February of '78. The dates that you see here are just sort of my particular favorites, and I want to highlight just a couple. And those are mid-2017. Mid-2017, the United States starts to launch Block 3. Probably about June of 2017, I think, is the current schedule. Once Block 3 is finalized, roughly about 2023 or 24, maybe even sooner than that, and you see my date 2020 with a question mark, I don't know. It's entirely possible that we'll be able to achieve real-time positioning at the few centimeter level with no ground control. So the use of passive control goes away. The use of cores might even go away. But it's going to be important to understand that NGS is preparing for this right now and is looking for a whole new datum in 2022, which will be captured in the discussion, the fourth of these presentations that we're giving. So just a little bit of highlight here. The first commercially available GPS receiver, the Micrometer V1000s, the Coast and Geodetic Survey, National Geodetic Survey acquires them in 1982, cost of $250,000 a piece. And where are we today? Well, you know, it's simple, it's cheap, If you have the IQ of a belt, you can go out and perform high accuracy surveying. We also need to understand the integration of the other navigational systems, the Russian GLONASS, the European Galileo, which is actively being launched right now. The European Union anticipates 30 by 2019, and the Chinese, their system Beidou, they're also talking about 30 by 2020. It's as part of this process, it becomes more important to understand organizations like what I refer to as the International Gold Standard, and that comes from the International Earth Rotation and Reference System Service, and they're headquartered in Paris. This institution captures geodetic positioning data from institutions around the world, and from that they create the best global set of coordinates, commonly referred to as the ITRF, the International Terrestrial Reference Frame. The first was 1988, the most current is 2014. They utilize these 4 measurement systems: GNSS, primarily GPS right now, satellite laser ranging, VLBI, very long baseline interferometry, and DORIS, Doppler orbitography and radio positioning integrated on satellites. And from that, this institution gives us our Earth orientation parameters, how fast the tectonic plates are moving, how the Earth wobbles on its axis. And here's just one example of that process. They give us our velocity field, so we know from them how fast all the tectonic plates are moving. So the National Geodetic Surveyor works closely with the ITRF. Now, I mentioned previously the issue of World Geodetic System 1984, and I want to come back to that very briefly before we finalize this particular session. Because so many users, because they're acquiring GPS and much of the training that they might get says, oh, well, GPS works in WGS 84. And that's true. It is the native coordinate system for the global positioning system, but the vast majority of people have no idea how many different WGS 84s there have been. And increasingly, as users are demanding high accuracy positioning, if you're going to associate your data with that coordinate system, then you must be able to provide the associated metadata. So the most defined document for it is produced by the National Geospatial Intelligence Agency. If you just go online and Google nga.stnd.0036, it'll take you right to it. And in there, what you'll find is how many WGS 84s have there been? And I'm just very quickly going to run through them here. There was the original, and this is what everybody commonly refers to. Oh, I have WGS 84. Which was very quickly replaced by WGS 84 G730 with respect to the ITRF. Remember that ITRF thing? Then there was WGS 84 873 with respect to ITRF 94, and it goes on and on. Periodically, every couple of years, the Defense Department changes this coordinate system to be as close as possible with the ITRF. Today, that being defined as WGS 84 G1762 with respect to ITRF 2008. Yet, in their documentation, they still show the transformation, the realization to NAD 83 as zeros, which it is not. So this is a problem. If you think you really have WGS 84 and you're trying to compare that with something in NAD 83, you have to fully understand those relationships and to be able to provide some of the important metadata that supports that. So for example, unless you're doing autonomous position, you're probably not in WGS 84. You could get some control from the US Defense Department, but you see my note, good luck, it rarely ever happens. If you say you have WGS 84 and you're accurate to a few centimeters, if you're tied to ITRF, then you most certainly could do that. The bottom line is, in most cases, you're really working in whatever the local control is. Even your PC is just telling you, or your data collection service is simply telling you it's WGS 84. In most cases, you're probably working in NAD 83. If you do have WGS 84, then you need to be able to provide the iterations of the various metadata. So the epoch of the observation, the realization, so these are critically important elements. just to highlight that our national datum, NAD 83, remember I said it was defined as Earth Geocenter as best we could define it given the technology of the 1970s. Our knowledge of Earth Geocenter today offsets NAD 83 by about 1.5 meters for the conterminous US. And here I've just picked one particular continuously operating reference station, happens to be in York, Pennsylvania. And if you just look at the difference in the X, Y, and Z Earth-centered, Earth-fixed coordinates, you look at the three-dimensional difference, you see 1.6 meters, so it falls right in there. This is a part of the process that NGS needs to resolve and will resolve with the new datums planned for 2022 that'll come along in the fourth session of this. So it's important for users out there to understand and provide accurate information about the metadata, the coordinate systems, the units of measurement, and the accuracy of data. Mind you, the accuracy of values, whether it's horizontal or vertical, is not the number of digits to the right of the decimal point. It has nothing to do with accuracy. It's how accurate were your measurement capability. 1 centimeter, a tenth of a foot, a few hundredths of a foot, whatever it happens to be, and to provide that. In this particular case, I've given you just a couple of images of what I refer to as some bad metadata, so that you'll have maybe something to go back and look at. And one that I particularly like, a beautiful little north arrow that a surveyor put on a plat, but it says it's relative to NAVD 88. Well, that's a vertical datum. It has nothing to do with horizontal. How do you know where north is with respect to a vertical datum? Or this particular one, benchmark, top of concrete bound, 73.68 GPS datum. Well, what's that? I have no idea. And regrettably, these are the kinds of things that we commonly see. I've gone through a complete definition of the datums, but realize many of the elements that I've talked about could be further explained to greater detail, and very likely many of you out there are going to want some of that. So you're going to need to find some other resources to go into greater depth. But as I always say when I finish a presentation, good coordination begins with good coordinates, and hence the use of GNSS, and geography without geodesy is a felony. So thank you for taking the time to review this, and I hope you will look forward to the other two presentations we're doing on vertical datums and the new reference frame planned for 2022. Thank you very much.